Hey everyone, and welcome. So, have you ever looked at a geometry problem and just felt this immediate wave of panic? Trust me, you are absolutely not alone. For a lot of us, geometry kind of feels like this totally alien language, right? Just a bunch of cryptic symbols and really rigid rules. But today, we're going to wipe that math anxiety right off the board. We are breaking down the incredibly cool world of circles and triangles. We'll build up your understanding block by block, roll by roll, until the whole shebang just clicks. Okay, let's dive into this.
You know, our human obsession with circles goes all the way back to the very beginning. I mean, picture early humans looking up at the night sky, seeing the moon and the sun, and recognizing that absolutely perfect round shape. But it wasn't really until the Greek era, specifically with mathematicians like Euclid, that we actually started putting names to the anatomy of a circle, figuring out its center, radius, and circumference. Fast forward to the Industrial Revolution, and that exact same geometric understanding was literally powering the world with wheels and steam engines. And today, circles are absolutely everywhere, from the tiny gears in your watch to, well, the pizzas we eat.
So, to conquer all this material, here is our game plan for today's explainer. First, we'll cover the anatomy of a circle. Second, the rules of congruency. Third, triangle types and their properties. Fourth, the essential circle theorems. And finally, we'll put it all into practice by constructing a circumcircle. All right, part one, anatomy of a circle. Let's look at the inner workings of roundness. Now, you probably already know about the radius and the diameter, right? But the real star of the show in geometry is actually something called the chord. A chord is literally just a straight line segment that connects any two random points on the edge of a circle. Imagine you're drawing a bridge straight across a circular lake, from one shore to the other. Now here's the cool part. If you keep drawing those chords closer and closer to the middle of the lake, eventually one of them is going to pass right through the exact center point. And the moment it does, it transforms into the longest possible chord in the entire circle. And we have a special name for that: the diameter. Now, when you draw that straight chord, it essentially slices the circle up into pieces. The curved outer edge of the circle, that's called the arc. But the actual physical space inside, that specific slice of area that gets sandwiched right between your straight chord and the curved arc, that is called the segment. It's really crucial to lock this vocabulary in right off the bat. The chord is the straight line, the arc is the curve, and the segment is the actual slice of space trapped in between them. Okay, moving right along to part two. The rules of congruency, or identifying identical twins. Think of congruency as the mathematical word for exact clones. If I hold up a 10 rupee coin and a 5 rupee coin, sure, they're both circles, but they're different sizes. Not congruent. But two shiny new 10 rupee coins, they overlap perfectly. True congruency. Now, while circles are super easy to check, triangles are, well, they're a bit trickier. So mathematicians came up with 5 highly specific rules to prove, beyond a shadow of a doubt, that two triangles are identical twins. First up is SSS, which means all 3 sides match perfectly. Next is SAS, where 2 sides plus the angle trapped right between them match. Then we have ASA, that's 2 angles and the side trapped between them. Moving on to AAS, which stands for 2 angles and 1 outside side. And finally, RHS, which is a special rule just for right-angled triangles. You check the 90-degree angle, the long hypotenuse, and one other side. If even one of these 5 conditions is met, boom, you got guaranteed identical twin triangles. And here is where it gets really good. Once you prove 2 triangles are identical twins using any of those rules, you unlock what is basically the ultimate superpower of geometry, CPCT. That stands for corresponding parts of congruent triangles. It is the undisputed brain of congruency logic. All it really means is that once 2 triangles are proven to be congruent, every single other matching part, every side, every angle is automatically equal. It's like a skeleton key that unlocks and solves almost every complex proof you're going to face in this topic. All right, on to part 3, triangle types and properties. Let's categorize these geometric shapes. Now, what's really interesting about how we categorize these triangles is that we can organize them either by their sides or by their angles. Looking at the sides, we have equilateral, where all 3 sides and angles are perfectly equal. Then there's isosceles, where just 2 sides are equal. And fun fact, that magically means the 2 angles opposite those sides are equal too. And then we have scalene, where absolutely nothing matches. Total chaos. Now on the angle side, we categorize them as acute, where all the angles are tiny, under 90 degrees. We have right triangles, which feature exactly one 90-degree corner, and obtuse triangles, where one angle leans way back and is greater than 90 degrees. So the absolutely crucial point to remember here is this magic number, 180 degrees.
This is the angle sum property. And honestly, it doesn't matter how weird, wide, or squished your triangle is. It could be scalene, right, obtuse, whatever. If you take the 3 inside angles of any flat triangle in the entire universe and add them up, they will always equal exactly 180 degrees. Literally no more, no less.
Let's jump into Section 4, Essential Circle Theorems, the geometric golden rules. I know theorems can sound super intimidating, but we're going to group them logically. They're actually just converse twins, basically geometric rules that perfectly mirror each other. Let's look at our first set of twins. The forward rule tells us that if 2 chords are the exact same length, they will create the exact same angle right at the center of the circle. The reverse rule, or the converse, is literally just reading that backward. It says if you have 2 equal angles at the center, the chords making them absolutely must be equal. See? It's just one idea flowing in 2 different directions. We just cut our cognitive load right in half. And this brilliantly illustrates our next set of twins, which deals with chords and center lines. The forward rule here, if you drop a straight line from the center that perfectly cuts a chord into 2 equal halves, meaning it bisects it, that line is going to hit the chord at a perfect 90-degree right angle. And the reverse rule, if you drop a line from the center at a 90-degree angle, it acts like a laser beam and automatically slices that chord exactly in half. They just pair up perfectly. Okay, our third set of twins is all about distance. If you have 2 chords that are the exact same length, they will always be parked the exact same distance away from the center of the circle. Conversely, if 2 chords are the exact same distance from the center, they have to be the exact same length. Now, let's take a quick second for a bonus piece of logic to really lock in here. If you take a chord and push it closer to the center, it gets longer. The closer a chord is to the center, the longer it is. Now, let's talk about what is perhaps the most powerful theorem on this entire list, the double angle rule. If an arc creates an angle at the dead center of the circle, and that same arc creates another angle all the way out on the far edge of the circle, the center angle is always exactly double the edge angle. And because of this magical little piece of geometry, if you draw an angle inside a perfect half circle, a semicircle, the angle on the edge will always, without fail, be exactly 90 degrees. Let's bring back our magic number from earlier for these final theorems. A cyclic quadrilateral is just a 4-sided shape that's completely trapped inside a circle, where all 4 of its corners physically touch the circle's outer edge. The golden rule for this shape, if you add together the opposite corners, the angles staring directly across the shape at each other, they will always sum up to exactly 180 degrees. Let's move to Section 5, Constructing the Circumcircle, and see how this all builds together. We are going to turn these abstract rules into physical reality. Here is how we actually do it, step by step. Step 1, draw your initial triangle. Step 2, take your trusty compass and bisect 2 of the triangle's sides. Remember our theorem from earlier? Bisecting creates perpendicular lines. Step 3, draw those perpendicular lines out until they crash right into each other. That exact intersection point? That is your circumcenter. Finally, step 4, put your compass on that center point, stretch it out to any corner of the triangle, and draw. Your circle will magically sweep around and perfectly touch all 3 vertices, and that proves that your center point is entirely equidistant from all the corners. Let's wrap things up with a really brilliant logic puzzle, straight from the source material. Imagine you just have 2 dots, points A and B. You could draw infinite circles that pass through both of those points, right? But what is the absolute smallest circle you can possibly draw? Well, think back to our chords. As you shrink a circle down, the chord connecting A and B gets closer and closer to the center, so the circle reaches its absolute smallest possible size the exact moment that line segment AB passes directly through the center to become the diameter. It's like a giant puzzle coming together. And that brings us to the end of our geometric journey. We have gone from the ancient Greeks staring up at the moon all the way to practically constructing complex circumcircles, and we did it all by just following a few logical rules. You see, geometry isn't just a bunch of formulas in a textbook. It is quite literally the hidden architecture of the universe. So I'm going to leave you with a challenge. Look around your room right now. Where can you spot circles hiding in plain sight? Can you visualize their chords? What about a tangent? Once you learn how to see the world through the lens of geometry, it will absolutely never look the same again. Thanks so much for joining me on this explainer, and keep exploring.